much for inviting me. It's always a little terrifying being in an auditory conference because once trained in vision, one always feels on slightly on, it feels like being on slightly on enemy territory, but a very, very friendly enemy. Is that fair? Yeah, that's fair. Okay, so what I'm going to describe is the work I've been doing for many, many years. She's very kind to not say how many years, studying how at a certain point you just stop. Work I've been doing over many years studying how blind people perceive the world. And what I'm interested in is the fact that not only are they missing a sense that takes up about 25% of the brain, but they're also living in a world that was designed by and for sighted people. And so what I'm going to talk about is the sort of modification that makes tasks like these possible. One is an example of someone crossing a road, and normally I have to kind of go into great detail explaining that the fact that there's a car behind her as well as a car in front of her. So if you're trying to stop cross a road, when cars see your cane, they'll stop because people are civilized, mostly. But she has cars going behind her, and so of course you guys all know that it's very difficult to tell those sounds apart, and so it's going to be very difficult for her to know when all the traffic has stopped. But nonetheless, she can successfully cross the road. And this other case of blind football, what I want to point out is they're not just chasing the ball, which has a jingle in it. You can see that one guy is kind of, I think it might be a foul, pushing the other guy aside. He clearly knows the other person's there, so he's keeping track of multiple objects. And so these are examples of the kinds of skills that blind individuals have that we really don't, especially not the football, not me. Okay, so what I'm interested in is you have this brain and you have this world that's full of vision and sound, and you have these babies that are born into some sort of bright buzzing confusion. And what happens when these babies are developed entirely using audition? So I'm really just talking about early blind individuals here. And I'm going to start I've got two talks really crammed into one. And depending on how fast I go and how bored you look, you'll get the second half or not. If you look really bored, you get the second half as a punishment. So the first half of my talk, I'm going to talk about two areas. One is this area HMT+, and I know you're all vision people, so you probably are completely unaware that this is a visual motion area. It responds to visual motion. I'm just kidding. I know you know that. It responds to visual motion, and it responds even when you imagine visual motion. And the other is this area, planum temporale, which especially in the right hemisphere is thought to be associated with tracking moving objects in space. Okay, so the question is, what I'm going to talk about in my first half, I'm going to give you the answer now, and you can just have a little nap, is that visual area HMT is intimately involved in auditory motion processing in early blind individuals. I'm going to show that this is a developmental adaptation requiring blindness early in life, that it seems to supplant the auditory motion area, the right planum temporale, and that suggests that there's competition between cortical areas for cortical role. And then finally, when you look at the computations that are happening in this area, in terms of behaviorally understanding auditory motion, I'm going to argue that both early blind and sighted individuals use space-time filters, and that the better performance of early blind people is due to better readout. So there you go, we're all done. Okay, so as I've said before, there's this area MT. That's weird. Okay, there's this area HMT. Normally there'd be a video, you'd see a little picture of HMT popping up. Don't worry about it, moving on. You all know where MT is, right? It's kind of in the vision-y bit. So years and years ago, a really talented postdoc of mine who ended up at INSERN, she was actually with me and Christoph Koch, she was curious about whether for early blind individuals, this area HMT might light up for auditory motion. There had already been a few studies suggesting that, but nobody had kind of really nailed this down because it's incredibly difficult to localize MT in a blind individual. At the time, our alignment methods weren't great, and also MT actually varies in location quite a lot between humans. And she had this really clever idea of looking at sight recovery subjects. So these are people who are blind, either at birth or from early in life, and then due to kind of a transformation medical kind of ophthalmological practice, they get their sight back when they're, in this case, they were both in their kind of 40s or 50s. So one of them was blind from 3 to 43, and the other was blind from birth until 40. So they're lacking early visual experience, and then they get it back at 40. And what we knew about these patients is that even though their vision is incredibly impaired, they are capable of seeing visual motion and interpreting it. Okay, so we think that their MTs are still active. So she ran a really simple experiment. The visual stimulus was simply dots that were either radially expanding or contracting, just sort of standard moving dots. And the sound was just little sound sweeps going either from left to right or right to left, and so on and so forth. And participants did it, sighted subjects closed their eyes. And this is what you get in the sighted subjects. The yellow shows the responses in the areas that are responding to audition alone. And again, this was early days of scanning, so this is not great data. The blue shows areas that are responding to the visual motion stimulus, so there's MT there. But what you see is that there's almost no areas of overlap between the audition and the vision for these stimuli, okay? And you might, what you also might notice is there's a little kind of yellow area that's kind of just anterior to MT. That's the auditory motion area. Olivia Collignon later did a beautiful study kind of identifying that area very clearly in a bunch of sighted people. But what we're not seeing is a sort of overlap between these auditory and these visual responses, which would be shown in green. However, when you look at sight recovery individuals, what you see is a big auditory response, and within that, there's an area that also responds to vision. So it looks like this visual motion area has been colonized by auditory motion. They're kind of like hybrid cars. They run on gas and electricity, okay? So that was a kind of really elegant and nice study. The question is, was it really auditory motion, or was it just sort of any sort of sound at all? And so we ran a bunch of extra studies. We compared ITD motion, so interval temporal differences motion, interval loudness differences motion, volume changes, so it's just getting louder and quieter, an FM sweep, or speech versus backward speech. And what you can see is that this area MT is really responding to the motion and nothing but the motion. It's not volume changes, it's not complexity, it's not frequency changes. So that was kind of nice. So the next question is how, we wanted to kind of just start, what I'm going to start doing from that basic point is start diving into kind of what are the computations that are underlying these auditory motion responses in area MT. And what I wanted was a task that kind of reflected this blind experience. And the idea from this task actually came when I was driving to work, and there was a woman on an intersection, and as I described, I kind of noticed her, and I was like, that is a really difficult task, because how does she tell the difference between the things in front and the things behind? And I actually stopped the car and ran back to kind of watch her. But by then she was already gone. So, and then I stood on this intersection and shut my eyes, and I was like, I would have starved to death on that intersection. There was no way I was ever going to cross the road. This is not a picture of her. This is another picture I found, but it really replicates what I saw. And it was like, okay, I would starve to death on this intersection, and she was out of there like a bat out of hell. So how did she do that, right? How did she get off that intersection? How did she tell that these cars had when to go? So we developed a task that's a bit like that. It was a bunch of kind of white noise, that were going, and they were in different noise bands. So you have kind of high frequency noise bands that are kind of like little hybrid cars, and you have low frequency noise bands that are kind of like trucks. And they can go either leftward or rightward. And they were kind of staggered in front and behind you. So it was a bit like standing in the middle of a freeway, except nobody really has a direction. There's no lanes, right? Everyone's just going. And you can either have all of them going to the left and all of them going to the right, and that's easy, and even I can do it. Or you can have half of them going one way and half of them going the other way, so there's no net direction of motion, and then you just guess. Or you can have 6 going one way and 8 going the other way, and that's really, really hard if you're sighted. Okay, now there's gonna be 8 of these because we're doing it in the scanner. Okay, so there are 12 of these. You probably can't hear the motion, but with ear things you can. And what you can hear is that unless you can get the motion signals, those cars don't separate out very well. So you're really tracking 12 objects at once. So you're trying to decide the net motion. What way is the freeway going? Is everyone driving into work? Is everyone driving away from work? And when you have 6 out-of-gate cars going in one direction or another, for sighted subjects, that's really difficult. You're like 68%. I'm actually worse than that, which is pretty normal for me. And if you're blind, it's a super easy task, and you're really good at it. And so we figured, like, okay, this was work done by Fang Zhang, who's now a professor at Nevada, UNR. And so this is a good task, but we've got a task that's really tapping into the kind of skills that blind people are using and are good at. So now we take this task and we take our brain, and what we're going to do is something called multivoxel pattern classification. Am I going at the right speed? Am I going too fast, too slow? Too fast, too slow? Just right? Just right. Okay. Goldilocks. Okay, so what we're going to do is we're going to take this area, any area, take an area, any area. We'll just take a bit of the brain, and there's a bunch of voxels in that brain. Okay? Now, overall, that area is going to respond the same to leftward motion and rightward motion. Let's pretend it's HMT and we're doing visual motion in a sighted subject. It's going to respond the same to leftward motion and rightward motion. But the idea is that, the neurons that are tuned for leftward motion might be preferentially selected to certain one kind of vasculature, and the neurons tuned for rightward motion might be preferentially connected to another kind of vasculature. And the pattern of responses is going to be very, very slightly different between leftward motion and rightward motion. So if I average a ton of trials with leftward motion together, I get one pattern. If I average a ton of rightward motion together, I'm going to get a different pattern. And then I'm going to take a test trial. I'm going to say, which pattern does this look most like? And if you kind of peer at this, you might say, well, I think it looks more like the red arrow, which is, I don't know what direction it's going for you because I'm all turned around and I can't do that kind of flip-flop, but the red arrow. I think it looks like the red arrow, which I think is going to the left. And if you get it right, then you got it right. And if you get it wrong, then you get it wrong. And if you get over 50% correct, because this is a two alternative choice, then it means that that brain area carries some information about direction of motion. Okay, that's MVPA. So we started by doing this in sighted subjects for auditory motion. And what you can see is that in sighted subjects for auditory motion, they're at chance. And again, that makes sense. We know this is a visual motion area. It's not an auditory motion area. Some people in this audience might disagree with me, and we can have a knockdown fight about that later. But right now, I'm on the podium, and I say this is a visual motion area. And you're going to have to come to the podium to get me to change my mind. Drag me off here. It's kicking and screaming. For early blind individuals, on the other hand, when they're doing this task using an auditory motion stimulus in MT, they're classifying it above chance. What happens with late blind individuals? Well, they're at chance again, right? So here are individuals who have normal visual development, then they become blind. They had been blind for at least 10 years, so they've been blind for a while. Still, they're acting like sighted subjects. So that implies that this is kind of developmental adaptation. And again, that's consistent with our sight recovery subjects where they do show this effect, just like the early blind individuals, even though they have been sighted for at least 10 years at this point. Okay, so this is something that happens in development. Okay, now let's look at planum temporale, and we're just going to look at the early blind and the sighted subjects for now. So again, in the planum temporale for auditory motion, for our sighted individuals, they can classify the direction of auditory motion in planum temporale. And again, that makes sense. It is an auditory motion area. The weirdest thing, and I think this is the weirdest result I've ever had in science, but it's actually, again, Olivier Collignon has replicated this, which was really nice, is that you can't, in blind individuals, it doesn't classify auditory direction of motion in the planum temporale. So that area has dropped out from doing auditory motion processing in blind individuals. And that has left me with a mystery that means I can't retire yet, which is, what is it doing? We know it's still an auditory area. It responds to auditory stimuli, but it no longer seems to have this selectivity for auditory motion. And, again, feel free to come to me with suggestions, because I would love to know. If we look at late blind individuals, again, auditory planum temporale seems to be a developmental thing. So in late blind subjects, auditory planum temporale, I'm just going to call it PT. PT classifies direction of auditory motion, and we didn't actually have, so there classifies direction of auditory motion. So that's all consistent with this story, that there's a weird competition between MT and PT, and in development, if you're blind, somehow MT is taking over the role that PT usually has. And I'd like to point out this is actually pretty interesting. We are very used to the idea that you have a cortical area and inputs compete for competition to be represented in that area. That's the kind of classic idea of plasticity. That's not what's happening here. Planum temporale is still getting its normal inputs. What's happening is two separated cortical areas are competing for cortical role. And there's a little bit of a hint in literature from things like stroke that this can happen, but it's really pretty understudied phenomenon. Okay, and then at some point, somebody in a conference, and I feel bad because I don't remember who, so I can't give them credit, said, well, if MT is tracking auditory objects, then it should also be frequency tuned, because that's how you would recognize auditory objects in the world. And so Libby Huber did this really pretty study. So here are our sight recovery subjects again. We've defined MT very carefully using a visual motion stimulus. And then what she's going to do is she's going to present moving stimuli, which are, again, these little motion sweeps, but this time they're going to change in pitch between 100 and 4,000 kilohertz. So they're going to, can't really do it. So we're going to take these sweeps that are varying in frequency over time, and she had them in these kind of little staircases, they would kind of go up a bit, then they go down a bit, and that kind of creates these little sweeps. And so you present these sweeps, and you get a bold time course over time that's pretty slow, right? This is all taking place over 20 or 30, 6 minutes, but I'm going to show you 20 seconds of it. You have this bold time course. And then what you're going to do is say, well, okay, imagine if that voxel in the brain was tuned to, say, this frequency. How well does it fit the time course? And you'd all look at that, and you'd say, that's a terrible fit. And I would agree with you. So I shift it around, and I get another Gaussian and another bandwidth, and eventually I find the Gaussian and the bandwidth that best fits my data. And that's called a population receptive field, okay? So what it is it's a Gaussian. In your case, it's in frequency space, but it can be in any domain that you want. In vision, it would be in visual space. And it's the kind of Gaussian in space that best predicts the response of that voxel, in the same way as you have a receptive field if you're doing electrophysiology. Everyone's good? All with me? Great. Okay. So when we do that and we fit these perceptive fields, what we find is that we do have voxels in HMT that are frequency tuned in our sight recovery subjects, right? Many of them are frequency tuned in one of our participants, and a minority are tuned in the other. Now, the question is how do you decide if this kind of fit is good enough that you're really pretty confident that a Gaussian fits these voxel responses? And so we did basically a sort of simple bootstrap analysis. And what you find is that in sighted individuals in MT, that threshold there, that line is the 1% threshold based on our bootstrap. So we expect only 1%, if there's nothing there, only 1% should come over that red line. In the sighted subjects, nothing comes over that red line, so that shows that our bootstrapping is working. And again, HMT doesn't show frequency-tuned voxels in sighted subjects. In sight recovery subjects, we see a decent percentage of voxels come over that line, and the same thing for early blind. So what we're seeing is, in early blind subjects and in sight recovery subjects, we are seeing frequency tuning in HMT+, which is consistent with this idea that MT is helping to track objects. So then Woonju Park, a postdoc of mine who's just moved to Georgia Tech, taken a faculty position there, had this idea, well, okay, MT is taking over auditory motion processing. What we know about area MT is it has what is called spatiotemporal filters. So basically it has neurons that if you kind of draw them on a space-time plot, or kind of have these diagonal structures. Okay, they're also sometimes called non-separable filters because you can't calculate them by simply multiplying a Gaussian in the horizontal domain direction and a Gaussian in the vertical domain. The other, and the separable filters look more like that kind of checkerboard thing, okay? And in audition, this is often called space-time tuning as opposed to motion tuning, right? So the question is we know that MT has these, these beautiful spatiotemporal filters. We know that it has these diagonal filters. Maybe in blind individuals, moving to MT kind of gives you access to those filters. All right, and before you get too excited, it doesn't. But it was worth a try. And you're still gonna come with me for the rest of the talk, aren't you? No one's gonna have a nap. Okay, so you've got these spatial temporal. The question is, are blind individuals gonna have a different perception of motion from sighted individuals? Now, there had been some evidence that sighted individuals also only have space-time filters, that they don't really have genuine auditory motion, that when you do auditory motion, you simply track objects moving in space and time. You don't have these spatiotemporal filters. And there's been a lot of elegant work, probably by people in this room, showing this. We used a different task to look at this based on a vision task. So I'm going to describe the vision task to you first, and then I'm going to describe the auditory task. So let's hope this works. If not, Jeffrey, then you're going to have to start my videos. Okay. Wait, hope. No, it worked. So what we're going to start with the signal, the stimulus was that bar moving down, and the noise was those kind of horizontal bars. And what you can see is that you've got this, that's the signal and the noise. And you can see that in that case, the ratio of the signal to noise was such that there was a lot of signal and there wasn't much noise, and it was pretty easy to see what was going on. Now, hopefully this is a different slide. Yep, there's the signal again. Here's the noise again. This time I'm going to change the ratio of the signal to the noise, and it's going to be much harder to see which direction the bar is going in. Okay. Now, what NERI shows is that if you kind of go back and say, okay, when did participants say it was going up, and when did they say it was going down, and you ignore the stimulus, because the stimulus by now is so, you keep participants at about 65% correct, so that stimulus is barely there. And you're really just interested in the noise. When did the noise lead the person to go up? When did the noise lead the people to say it was going down? What you find is that the noise produces this spatiotemporal filter. So the signal here is those yellow dots, shown in those yellow dots. And what it's showing is that the filter you're using to do this task has that spatiotemporal time, the filter you're using to do this task has that diagonal structure, okay, that we were looking at before. Kind of, so you can kind of, from the noise, you can infer what filter participants are using to do the task, right? If they're ignoring part of the spatial-temporal space, then that noise will have no effect on the response. If they're paying a lot of attention to that region of the spatial-temporal response, the noise will have a lot of effect on their response. Does that make sense? Okay. And so what we're going to do is the same thing, but we're just going to do it in audition. So here we have a stimulus that moves in space and time. We have white noise that is kind of moving around in space and time. What you'll notice, and this is going to prove to be really important, is the noise is wider in space than the signal, and it also starts earlier. So the signal is kind of embedded within the actual stimulus is longer and broader than the signal. And so the task people have to do is detect that signal in this space-time noise. And the first thing you'll notice here is that blind subjects are really good at this, and sighted subjects not so much. Actually, one of the problems in our running this stuff is that as sighted individuals, we'll set up a task, and then the blind subjects will all be at 100%, and we have to kind of titrate and titrate and titrate. It's quite difficult to actually design these stimuli. We probably need some professional musicians in the lab. They might be closer to the blind individuals. So yeah, you can see this as a huge difference in thresholds for the blind and the sighted individuals. And that makes sense, because blind people are often trying to track objects in noisy environments. It wasn't simply just that blind people are kind of better at doing auditory tasks in a kind of trivial way. What you can see is that difference. We actually ran 6 sessions of this with a couple of thousand trials each. They did this for 6 hours. And the difference between blind and sighted subjects doesn't go away. So this isn't a kind of a trivial practice effect. It's something you really have to spend a long time. You have to be blind or possibly a professional musician. But when we look at the filters, we don't see any major differences in shape between these filters, between sighted and blind subjects. Both of them are using spatiotemporal filters, okay? And you'll notice 2 things about these filters. One is very obvious, that the filters are just much cleaner in the blind individuals, and that implies that they have better signal to noise. And the second is, if you look at those group differences, you can see that the blind individuals are paying a lot more attention at the onset of the actual signal, whereas the sighted individuals are paying more attention at the onset of the stimulus. Remember, I told you that the stimulus starts and then the signal starts, both in time and space. And you can see the blind individuals kind of are more focused on the beginning of the actual signal and not the stimulus. And we can quantify this in another way. So we have here is a graph in the top. The gray triangle, that's the word triangle, is the stimulus onset. And the yellow triangle is the signal onset. And green dots are the sighted, and the purple dots are the early blind. And what you can see is the early blind dots are kind of shifted towards the signal, and the green dots are shifted towards the stimulus onset. And then we can quantify this signal to noise between the early blind and the sighted. And once again, you can see this big difference in signal to noise. So it's those two things happening. The filters are cleaner, or they're paying more attention to the filter and less attention to stuff outside the filter, and their filters are better located. Okay, you're going to get both bits of the talk. So aren't you lucky? So to summarize, I'm going to summarize what I started with. Visual area HMT is intimately involved in auditory motion processing in early blind individuals. It's a developmental adaptation, requires blindness early in life. You see it in early blind individuals, you see it in sight recovery individuals, you don't see it in late blind individuals. It seems to supplant the auditory motion area, right planum temporale, implying that there's competition between cortical areas for role. Both early blind and sighted subjects use space-time filters. So this move to MT doesn't result in spatiotemporal tuning the way we kind of hoped it would. But early blind subjects are much, much better at auditory motion processing, and that seems to be due to having filters that are located better and higher signal to noise. Okay, that's the end of the first talk. So now what I'm going to do, this is the scary bit, because I believe you guys know something about auditory cortex. So up till now, it's been like MT, and I know about MT, you don't know about MT. But now we're in auditory cortex, so this is the scary bit. We're going to talk about auditory cortex. And there's two titles to this talk. One is the effects of early blindness on auditory frequency tuning and auditory cortex. And the other is why are so many blind people piano tuners? Because it really is true. A lot of blind people are piano tuners. Now, there are many reasons for this, right? One is that there aren't a whole lot of jobs blind people can do. Like airplane pilot is out, right? So artist, also not a good idea. So they have a fewer selection of jobs to work with. The second is that, there are schools that are specifically to train blind people to be piano tuners. It's a good job. It's easy to train. It's easy to do if you're blind. So there's a school, I think, in Iowa that's specifically for blind piano tuners. So they're kind of shoveled into that. But even given that, the number of blind people who are either piano tuners or musicians is really, really high. And there's a beautiful paper by Gugo in Nature. I don't know how you pronounce Gugo. Someone can correct me later. In Nature, who basically says, okay, blind people have better pitch perception than sighted individuals. Okay. So what I'm going to argue in the second half of the talk is first that auditory cortex does have narrower frequency tuning in early blind individuals, but possibly not for static stimuli. And secondly, early blind individuals are better at pitch perception, but that doesn't seem to be based on narrower frequency tuning. Instead, it once again seems to be based on having higher signal to noise. Okay, so we're going to do population receptive field mapping again. This time we're going to, as well as using our motion stimulus, we're going to use a second stimulus. It's more kind of classical stimulus. So this is going to be a set of tones. They're going to just sweep up in frequency, kind of like a moving bar. Each of these kind of tones is actually a little Morse codey thing because you want to kind of get a nice rockin' response in your auditory cortex. So it's going to boop, 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 and every tone has a different Morsey thing. I can only do one Morsey thing for some reason. It's like I can only do one. But anyway, and once again, you have your bold response over time. You're going to find the Gaussian that best fits it. But now we're going to interest in two things. We're going to interest in the frequency that best fits that response, and we're interested in the bandwidth. Okay. So this work was originally done by Jessica Thomas, and what we showed is that you could see these beautiful frequency maps in the primary auditory cortex that go from high to low to high across Heschel's gyrus. And there was a beautiful talk earlier about the fact that Heschel's gyrus is complicated. And what we find is that, this pattern, you can see that these frequency maps align with Heschel's gyrus in a way that can be predicted by the morphology of Heschel's gyrus, even though it's complicated. Okay. So we kind of have these maps, and so what I'm showing you here is two sets of maps. One is, left side is sighted subjects. Nope, that's not right. The top is sighted subjects, the bottom is blind subjects, and you can see the maps to the two different kinds of stimuli. And you can see these are different individuals, so the maps aren't meant to look the same. But what we have done, and I think one thing that's really important when you do maps like these is these maps should be replicable across, not necessarily drastically different stimulus, but for example, let me go back up here. What you can see here for this map here, you've got S3 on the top and S4 at the bottom, is we have ascending stimuli, so it's and descent, and then we have one that's fit using both. And what you can see is that the maps look a little different, but they have the same essential structure across these different kind of stimuli. And the same is true for the other participants. So making sure that your maps are replicable, I think is really important, because the way the bold signal works, you're always going to get a rainbow, even if it's white noise. So you have to make sure this is, your rainbow is replicable. So anyway, here we have 4 different subjects, 2 different stimuli, and we're interested again in this population receptive field. And again, I'm going to hammer this home because it's super important. The population receptive field is not the same as the receptive field. Because a population receptive field represents the collective response of thousands, many thousands of individual receptive fields. Okay, because it's in a voxel, and a voxel, no matter how big it is, it's still going to contain thousands and thousands of neurons. And so even if your receptive fields are narrow, if your voxel is so big that the frequency dispersion in that voxel is pretty big, you're not going to see a difference in your frequency population, the bandwidth of your population receptive field. So 2 things have to happen. You have to have to get a narrow bandwidth in your population receptive field. You have to have narrow bandwidths in the individual neurons, and they also have to be all tuned to pretty much the same frequency. If you don't, you're just going to get a kind of really big population receptive field, and you're not going to be able to tell these two apart. Does that make sense? So what we're interested in is Q, which is this tuning, and because you auditory people are just trying to confuse me, the smaller Q is, the bigger the receptive field, and the bigger Q is the smaller receptive field. So as far as I'm concerned, all these graphs are upside down, but I won't stand on my head. And so here we have our blind subjects and our sighted subjects, and this is data that actually I was collected at Oxford with the help of Holly Bridge. And the nice thing about collecting that at Oxford is she has a really expensive scanner that can do 1.2 millimeter voxels, and we didn't. We still don't. And so these are really small voxels, and what you can see is our blind individuals have much narrower bandwidths than the sighted individuals. Okay, this was for the moving stimuli. And you can see that both in primary auditory cortex and in secondary auditory cortex. We did the same thing on a fairly crappy scanner. We've got a slightly better one now. And we have 3 millimeter voxels. And what you can see is that we do see a difference, again, in tuning, and certainly in primary cortex, but that difference is much smaller because, again, we've got a much bigger spread of frequencies in our voxels. And we see it again in secondary. What's interesting is that we don't see that difference for the static sounds. So we don't see a difference in tuning for static sounds. Now, again, we were struggling with our scanner, and this is something I'd love to repeat. But for now, we're going to assume that that is correct, or at least that we're not seeing a massive frequency difference, tuning difference for these static sounds. Which leads us to, okay, if you're not seeing a huge difference in frequency tuning in primary auditory cortex for static sounds, let's go back to this idea that early blind individuals are really good at pitch perception. Okay, and so we started actually, mostly because I didn't know what I was doing, with a notch task. So I was like, okay, let's get, really simple, this is the most basic, frequency discrimination task you can have. And so we did notch task, and we compared our blind and sighted individuals, and you can see there's absolutely no difference between them. And then an auditory psychophysicist looked at me like I was a moron and said, that's a measure of cochlear tuning, you know. So we were like, okay, this is our control experiment. So what we can show, what's really nice about this is it shows like, okay, the cochlear tuning of our blind and sighted subjects is identical. Now let's go and like measure something that has something to do with the brain. So, and what we also find is that the years of musical experience has no effect on the notch task. Now that is inconsistent with some earlier studies in the literature, which show that musicians, the effect of musical experience on musicians, you can see an effect for this notch task. I'm happy to talk in the discussion why I think we get different results here. Okay, so there's no effect of blindness or musical experience on the notch task, which we think is kind of based on cochlear tuning. So now let's do the classic Gugo task. So we've got two pitches, boop, boop. The pitches vary either in how fast they are, boop, boop, or they vary in how big a frequency difference there is between them. And we're going to look at the percent correct. And what you can see is there's kind of two ways they vary. Remember the frequency difference. So if the frequency difference is very small, boop, boop, then people are pretty bad. They're at 60% correct. And as the frequency difference gets bigger, boop, boop, people get much better at it. But the blind individuals get more better at it than the sighted subjects. There's also the way you can titrate the difficulty task is the duration, how long these tones last. And what you can see is that the blind subjects are better for all of these faster tones, okay? And so we actually fit this data with a model. We basically used a signal detection model, and I'm gonna sweep all of that under the rug. And basically this model allowed two things to vary between the sighted individuals and the blind individuals. One was the frequency tuning, and the other was the signal to noise. And what we find is we see no differences in frequency tuning between the blind and sighted groups, or if there is one, it's tiny, but we do see a big difference in that signal to noise. So it looks like the reason blind individuals are better at this task is they have lower signal to noise, not narrower tuning. And when we look at years of musical training, we get a really nice result. We see that for the tuning, there's no effect of years of musical training. But when we look at the signal to noise, we see an effect of musical training in both the blind and the sighted groups, but the blind individuals are always better than the sighted groups. So there's a kind of two effects happening. One is years of musical training that kind of operates similarly across both groups, and the other is this effect of blindness. That is just a kind of downward shift, and that's kind of pretty. So both blindness and years of musical training affect signal to noise in a pitch discrimination task, but this seems to be driven by changes in signal to noise. It's not driven by changes in bandwidth. Okay, so I'm going to summarize the second part of the talk, which is that auditory cortex does have narrower frequency tuning, but maybe not for static stimuli. And that doesn't seem to be what mediates performance in an auditory frequency task. Early blind individuals are indeed better at pitch perception, but this is based on having higher signal to noise, not narrower frequency. And in general, what this suggests is that much of the enhancements you see in early blind individuals is actually due to better readout. And kind of what we want to do going forward is sort of try to pin that down a little bit more precisely, because I realize it's pretty vague. All right, thank you.
So thanks very much, Ione, for the great overview of your work. We're open for questions, and we can throw these things. Or
I'm not throwing it. I can't throw.
Maria? I'm not a good thrower, so. Is it on? Yeah, he will turn it on. So. Oh, here we go. Okay.
Thank you for a really interesting talk. When you say signal to noise differences, I immediately think, well, is it attention? Are they just better at focusing attention? And so in the MRI data that you've shown, I haven't seen any, but I don't know, maybe have you looked at attention related activation?
We have not really studied attention in early blind individuals. It's a little tricky because you can't shift it to another modality, right? You only have audition, so they're always going to be, they can only really pay attention to an audition. So you can, shift what direction. You could certainly look for, actually, I have a grant in review right now, which would actually look at things like spatial attention and featural attention in early blind individuals. I don't know anyone who has actually looked at it. When we run our participants, we select pretty carefully. These are not, subject pool people. They're pretty motivated, and they tend to be kind of professional subjects, even our age-matched subjects for the blind individuals. So I don't think it's attention. Again, and another reason I don't think it's attention is for the notch task, we don't see a difference. So that's a kind of very similar task in terms of how boring it is, and we see absolutely no difference there. But we see this big difference for the pitch task, and they're equally boring. I do think they have a slightly lower boredom threshold. They find it more fun than the sighted subjects, but we select for that with our sighted. We choose really motivated.
Can I follow up? The notch one, I mean, if they are doing, as best they can, and both groups are, then I wouldn't expect a difference. But it may be that in a situation where there is noise, it may be that and I'm saying this with zero intuition because I have never worked with populations that are not hearing. Could it be that blind populations, but could it be that they're just better at suppressing a noise and focusing on a signal? So it's a kind of attention, but not a motivation difference.
Yeah. So when I say, when we describe these filters and we say that blind individuals have these filters that are better matched to the signal onset and less, and so they're actually, you could call that I think that's may not be difference in the underlying filters. It might, like innate filters, it's that they know which neurons to listen to. Now, I would not call that attention, but if you want to call that attention, then I would agree with you, right? But that's what I would call readout. So what you're calling attention is like, are you paying attention to the right neurons? You call it attention, I call it readout, but I think we're talking about the same thing.
Thank you, that was a great talk. I have two questions, both about the motion task. First, I'm wondering if you noticed any individual differences in the use of binaural as opposed to monaural cues, because you have both when you have a moving stimulus. And the second, and maybe more interesting question, is how does the auditory information get from the cochlea to area MT? Because I might have thought, well, of course it would go through the auditory cortex and then to this posterior region, but you showed that the planum at least doesn't code for spatial information in those people. So how do you think about that?
How does that work? Yes. The first question is, we haven't really looked. We tend to focus on stimuli that are as kind of vaguely realistic as possible rather than like pure ITDs or ILDs. In fact, most of our stimuli now, we actually use real world sound models. So we include things like Doppler, which is, so we haven't ever looked at that sort of thing. The second question is really mysterious. What I would say is that, and this will go back to your question, I'm not sure we see these effects when they aren't attending to the motion stimulus. I think if you have them, we've had a student who ran it and they weren't attending to the motion stimulus per se. They were doing a loudness judgment rather than a motion judgment, and we couldn't classify anymore. And so that's, again, something I'm trying to look into. So that would suggest that the motion computations are happening somewhere else, and it's actually getting fed back into MT. But there's still this mysterious fact that planum temporale, it's not coming from planum temporale as far as we can make out. And so it's kind of mysterious. So the next stage is sort of doing something like EEG or MEG, where we can kind of look at the timing of the signals. But that's not my expertise. So.
Thanks.
Right, over there.
This is more of a question about your control subjects. What was the extent of asymmetry in platinum temporale, was it predominantly, it seems like based on your figures, it was predominantly right. To what extent was it lateralized? And was there any participation with the parietal lobe?
I don't look at parietal lobe because it scares me. You're welcome to have our data. That's a hard no. I think it's a while ago. I think we occasionally see it in the left, but it's not as strong. What we haven't done is looked at anything like handedness and see if it flips or anything like that. I can go back and look. My feeling is we sometimes see it in left, we sometimes don't, so we tend to just focus on the right.
Hi, hello. Thank you for the nice talk. I have kind of a bit naive question. So I'm just curious, what would happen if the population, like you're working, like just have like blind from one eye? Like I don't know the incidence about it. Maybe it's a hard population, but what would have the effect of your result? Maybe for the motion part.
I think, my own view is that you have two eyes for redundancy, right? We shut one eye and I can still pick up a cup, I can drink, and put it down again. All right, we work fine with one eye. Stereo vision is not that important. Lots of people don't have it. Lots of people don't even know they don't have it. That's, color is also completely useless. It's just there for fun. You're right. Stereo is there for sewing, and color is there to make our lives more interesting, right? Seriously. I'm going to get mobbed here. So I think they would behave like sighted individuals, right? People with one eye are people who can see, right? The main thing that you can't do with one eye is play rough sports like baseball, because you will never be allowed to do it, because if you lose that one eye, you're in trouble. But that's it. If there's any one-eyed people who really disagree with me, they can shout at me now.
No disagreement here. Thank you so much for the talk. I have about 1 million questions, but I'll just keep it to one. I was thinking the whole time about the studies where they forced auditory input into auditory or visual input into auditory cortex, and one of the things they saw was that lateral pulvinar was suddenly now connected in a way it had never been before. So I'm wondering if you have any sort of connections in some of these formerly visual areas to like various subcortical auditory structures, or if you've seen any kind of activation of subcortical auditory structures or visual structures, sorry, that would in these blind individuals.
Actually, coming back to that question, probably a better answer is we did a collaboration with Holly Bridge at Oxford again, that 70 scanner. Oh, that 70 scanner. And I love Holly too. She's also very cute. And what we actually found is that the superior colliculus, we do see responses in early blind subjects. And I think we also saw the pulvinar. And those results, we did it in UW and we did it in Oxford, and their result, the results weren't entirely aligned, but that was again probably because we hadn't got a very good scanner. But yeah, we do see some subcortical reorganization happening, we think. It's really hard, those areas. And then I tried to look at MGN and LGN, but the postdoc broke. It's really hard to identify those areas, so I had to stop. You can't break your postdocs, it's not good.
Other question front?
Yeah, this is related to a bunch of these questions. There's this very common idea that you hear that kind of cortex is cortex. It's sort of, there's a canonical circuit, and what really determines function is the anatomy, what things are connected to which other things. Like some of your results seem to violate that idea. So I'm sort of, you know what I mean? And that your results, the naive interpretation is that, maybe function is function, and so maybe other things sort of work around that. So I'm just curious your take on that.
Okay, so there's sort of two, okay, let me see if I can summarize this really quickly. And this was, again, the motivation when we started this, is this beautiful idea of the metamodal cortex, right? That the idea that areas don't necessarily, maybe area MT isn't really a vision motion area. It's an area that wants to track moving objects in space. And for those of us who are sighted, the best source of information is vision. So that's why it's a vision area. It has a functional role, the sensory input, it just chooses what's best. And that's what explains this cross-modal plasticity. More recently, Marina Bedney has come up with this really interesting hypothesis of the pluripotent cortex, which is this idea that the computations in the gray matter sheet are kind of generic, canonical, you know, it's a you add, track, divide, contrast normalization, so on and so forth. And really matters is the input that comes into it. And that kind of fits in with this ferret idea of, you know, rewiring, you know, if you send a different input in, those computations will just work with the input that you have. Then there's a third argument, which is the neuronal recycling hypothesis, which is that areas have specific sort of canonical circuits that are kind of specialized for that particular region. And so the reason why we see reading areas very close to the fusiform areas is that the canonical circuits in that area are really well designed for looking at fine detail. And it doesn't matter whether fine, and so basically you had this area that was designed for fine detail, you had to learn how to read, and you're like, okay, I'll do it here. And I think I'm probably belong to the neuronal recycling hypothesis. The issue I have with some of the, so I don't think cortex is just blob gray matter. I think that each area has specializations, but those specializations can be tweaked or recycled for other purposes if they need be. I said that would, but again, you know, these ideas are out there and everybody can come to their own conclusions depending on how amorphous you feel. But having seen how untrainable my children are, I think cortex is pretty hardwired, or I'm a bad parent. No, seriously, right? You know, there's no way this is just a blob of gray matter, because these kids are deterministic.
All right. Any further questions? We have room for one more. Ilya?
Hi, yeah, so for the encoding of sound direction, I mean, like in the auditory cortex, like the brown temporal, but there is quite some evidence that you use the differences, right, left, right. So this idea of opponent coding and all these things. So have you ever looked at that? Because also the decoding, you focus on one hemisphere, right? But actually decoding schemes that would consider both the hemispheres work much better. I was curious whether this is also in MT, then do you develop a sort of opponent coding?
Yeah, I guess I've always assumed that, you know, you have these interhemispheric connections, and so the computation is, you know, done by neurons that are in one hemisphere but are driven by, you know, both ears, right? So it's an opponent code, but it's got to be there's a cell, and it's got to sit in one hemisphere or the other because, you know, there's nowhere in the middle, and that cell is doing that opponent code there. So I think what we haven't, you do see, if you play a stimulus into the right ear, a bigger response in the left hemisphere, and if you play a stimulus in the left ear, you get a bigger response in the right hemisphere. So, you know, if we do that kind of gross level subtraction, we would be able to decode which direction. Well, we wouldn't be able to decode which direction things are going into because, again, this is a sweep, so
yeah, for
it's
the trajectory.
the sweep is much faster than the bold response. So
Still,
over each sweep, the responses in each hemisphere are the same. So it really, you know, it is a motion signal, not a loud. It's not that signal because that signal is too fast for us. Bold is slow.
All right.